Hello, we're going to look at notation for partial derivatives, and these will be for functions of two variables or three variables. This initial part is the notation that you can see. It's not meant to overwhelm you, it's just if you see any of these type notations, they all mean the derivative of this function with respect to the x variable. This is a lowercase delta. The derivative with respect to y, most of the time you'll see it written with a subscript y. If it's a derivative with respect to x, you'll see a subscript x. But anyway, this is just all the various notations you could see, but each row, those are the same way to write. They're different ways to write the same thing. If you're supposed to evaluate a partial derivative, this would be the direction derivative. It gives you the slope in certain directions with respect to x or with respect to y. Basically, you take your partial derivative and then you sub in the point that's given. Let's look at an example. Let's let f of xy be 3x minus x squared times y squared plus 2x cubed y. This function would represent a surface. Let's find the partial derivative with respect to x and then with respect to y. And once we do that, we're going to substitute in values for x and y into those partial derivatives. With a partial derivative with respect to x, we're going to make sure that we treat y as a constant and take the derivative of the x part of each term. For example, this first term is 3x. Its derivative will be 3. The second group of terms, you have an x term. The derivative of the x term would be 2x, and then you attach whatever's next to it. So that's negative 2x y squared. Notice the y does not change, only the x part has the derivative taken. And then finally in our third term, the derivative of the x part would be 6x squared, and then you just attach the y to it. If you go through the same function but take the derivative with respect to y, the first term has no y, so that's a 0. This would be considered a constant. There's a 0 here, I just didn't write it. In the second term, the y term would have a derivative of 2y, so overall it's negative 2x squared y. In the third term, we have a y. The derivative of y is 1 times 2x cubed is 2x cubed. Now that we have our partial derivatives taken, this is the rate of change of the surface in the x direction, the rate of change in the function in the y direction. So if we substitute in a number, 1 for x, negative 1 for y, you go through your partial derivative and you do exactly that. You appropriately substitute for y and x, and you'll get a numerical value. This is the rate of change at this point in the x direction for this function. And then f sub y, put a 1 in for your x's, a negative 1 in for your y, grand total 4. Let's look at another example. Let z be a function of two variables, x and y, defined as natural log of x times sine of x squared y. I kind of switched notation up a little bit just so that you're exposed to the different types, but this is still the partial derivative of our function with respect to x. Our first term has an x, derivative of natural log is 1 over whatever trails it, so it's 1 over x times the derivative of x, which is 1. times the second term. So it's derivative of the first times the second, we're using product rule, plus first times the derivative of the second. The derivative of the second term is cosine of x squared y times the derivative of the x part, 2xy. So this will simplify, and you don't have to simplify this. It's just if you wanted to clean it up a little bit, you have sine x squared y over x plus 2xy natural log x cosine x squared y. If we go back through the same function and take the derivative, this time with respect to y, and again it's product rule, so derivative of the first times the second. Derivative of the first is 0 because there's no y term, so this is actually considered a constant. Derivative of the first times the second plus first times the derivative of the second, which is cosine x squared y. And this time we're going to take the derivative with respect to y. Derivative of y is 1, so it's 1x squared. Cleaning it up, the first half goes away, so we have x squared natural log x cosine x squared y. Yet another function, this time we're going to do a substitution. We have a function of two variables defined as x times e to the x squared y. Let's find our partial derivatives, and then we'll make a substitution at the point 1 natural log 2. Derivative with respect to x, it's derivative of the first, which is 1, times the second, plus first times derivative of the second. For derivative of e, you make a copy of what you see, times the derivative of the exponent. With respect to x, that's 2xy. If you clean this up, it's e to the x squared y plus 2x squared y e to the x squared y. Substituting in our point, 1 goes in for x, ln2 goes in for the y variable here in our partial. So it's going to be e to the 1 squared ln of 2 plus 2 times 1 squared ln of 2 e to the 1 squared ln of 2. That's a mouthful to say, but once you get your partial derivative, it really is a matter of substituting in for x and y. E to the natural log of 2 is 2. 2 times 1 squared times natural log 2 is 2 ln 2. And then again, up here, this is ln of 2. E to the natural log 2 is 2. Cleaning this up, we have 2 plus 4 natural log 2. Our derivative with respect to y, back up here using product rule, we're going to do derivative of the first. Since the y is missing, that's 0, times the second, plus first times the derivative of the second. Make a copy, take a derivative of your exponent with respect to y. Derivative of y is 1, so that becomes x squared. Cleaning it up, this first half goes to 0. In the back half, we have x cubed, e to the x squared y. Substitute 1 in for your x, natural log 2 for your y, and this becomes 1 e to the natural log of 2. 1 times 2 is 2. Find the slopes in the x direction and y direction for the surface given by negative x squared over 2 minus y squared plus 25 over 8. And we're going to look at the point 1/2, 1, and 2 when we do that. So let's take the partial derivative with respect to x. This is the only term with an x. So its derivative is negative x. Subbing in 1/2 and 1, there's no z, so we don't put like a 2 in, but we sub in a 1/2 and a 1. There's only an x in that partial derivative to catch the half, so negative half is our x direction slope. Now down here in this first illustration, the graph of that surface is given here, sort of a elliptical shape. I've tried to halfway mark off the point half 1 and 2 with x, y, and z. But long story short, on this surface at this point, the rate of change is downhill at a rate of -half. Now let's look at the surface and take the partial derivative with respect to y. Our middle term is the only one with a y, and its derivative is -2y. The first and third term go to 0. This partial derivative with 1/2 and 1 subbed in is going to be -2 times 1, which is -2. In the y direction, so in the background I had the plane, but it's facing in the y direction, whereas in the first diagram it was a plane, a slice going in the x direction. But anyway, that surface in the y direction at that point has a rate of change of -2. Next example, find the slopes of the surface at the point 1, 2, 1 for the function 1 minus x minus 1 quantity squared minus y minus 2 quantity squared. The partial derivative with respect to x is chain rule, -2 x minus 1 to the first times the derivative of x, which is 1. Substituting in a 1 for x, we get 0. The derivative with respect to y, these first two terms go to 0, so that's -2 y minus 2 times the derivative of y, which is 1, leaves us with -2 times y minus 2. At the point 1, 2, sub a 2 in for y, you get another 0. Now both of these partial derivatives were equal to 0. If you were to graph this surface, what we'd actually have found is in the x direction and the y direction, the rate of change is 0. And we've actually found the top of that surface. The area of a parallelogram with adjacent sides A and B and included angle theta is given by capital A equals A times B sine of theta. Find the rate of change of area with respect to side A. The only term that has the A is right here. Derivative of A is 1, so we're left with B sine theta. Substituting in 20 and pi over 6, because all we have is B and theta, 20 times sine of pi over 6, that's 20 times a half, which is 10. That's the rate of change of area if A is the one that fluctuates. Find the rate of change in area with respect to theta, and this would be the change if theta was changed smaller versus larger. With theta, it's in the trig part of our function, that derivative is cosine theta. These two stay the same, so it's AB cosine theta. Subbing in our numbers, 10 times 20 times square root of 3 over 2. 2 cancels into 20 10 times, so we have 100 square root of 3. Let's look at a function of 3 variables. The partial derivative with respect to x, let's take it one term at a time. This one, the derivative of x is 1, so that leaves us 1y. No x, that term goes to 0. And we have another x here. Its derivative is 1 times z is z. This time, let's go through each term. Take the derivative with respect to y. Derivative of y is 1 times x is x. Derivative of y is 1 times z squared. No y, no derivative. It's 0. And then finally, with respect to z, no z, 0. Derivative of z squared is 2z, so that's 2yz. Derivative of z is 1 times x is x. Now let's look at another 3 variable function, z times sine of xy squared plus 2z. Our derivatives will involve chain rule. We have an algebraic term times a trigonometric term. So we will be doing product rule. Derivative with respect to x, derivative of the first times the second. There's no x, so 0 times the second, plus first times the derivative of the second with respect to x. Derivative of sine is cosine. Keep your angle the same. And now, with chain rule, the derivative of your angle with respect to x, which is 1 times y squared. You'll also have to remember chain rule. That second term doesn't have an x, so it goes to 0. Cleaning this up, your first half disappears. The second half is y squared z cosine of xy squared plus 2z. Partial derivative with respect to y, our first term has no y, so its derivative is 0 times our second term as is, plus first term, which is z, times the derivative of the second term with respect to y, that's cosine of xy squared plus 2z, times the derivative of your angle with respect to y. Well, there's a y squared, its derivative is 2y, times x that's attached, gives you 2xy, and the second term has no y, so there's nothing else to put back here. First half goes to 0, 2xyz cosine of xy squared plus 2z. And finally, our derivative, the partial derivative with respect to z, again, product rule, derivative of the first, in this case it's 1 times the second, plus the first times the derivative of the second, which is cosine xy squared plus 2z, times the derivative of your angle with respect to z, which is going to leave you a 2. Sine xy squared plus 2z plus 2z cosine xy squared plus 2z. Let's let g of xy be a 2-variable function defined as 3xy squared minus 2y plus 5x squared y squared. Our derivative with respect to x, this first term has an x, its derivative is 1 times 3y squared. The middle term has no x, so its derivative is 0. I just didn't write anything. And then finally, our third term, the x term, has a derivative of 2x, so it's 10xy squared. The derivative with respect to y, go through each term one at a time. We have 2y times 3x, that's 6xy. The middle term, its derivative with respect to y is negative 2. And our last term, its derivative with respect to y is 2y times 5x squared, that's 10x squared y. Now, what we're going to do here is notice these subscripts are getting doubled up. These are called second partial derivatives. G sub xx means that we take our first partial derivative, g of x, which is this top one, and we take the derivative at one more time with respect to x. No x, that's 0. X here is 1 when you take the derivative times 10y squared. So the second partial derivative, g of x of, g derivative with respect to x, and again with respect to x, is going to come out to 10y squared. If we take that first partial derivative, g sub x, but then take the derivative of it with respect to y, we get 6y plus 20xy. So it's the first partial derivative with respect to x, and then take its derivative with respect to y. The first partial derivative with respect to y was 6xy minus 2 plus 10x squared y. We can take that partial derivative and take one more derivative and make it with respect to x. So that's going to give us 6y, 0, and 20xy. Notice that the second partial derivative is equal. That's going to be true for your functions of two variables. No matter which derivative you take first, if they're mixed, they will be equal. And then g sub y, that's how I'd say it. Derivative with respect to y is 6x, 0, and 10x squared. I hope this video helps you out. Please reach out with questions as you have them. I can be reached by email, phone, swing by the office if you need to, and I will do my best to help you out.